All right. Welcome, boys and girls. Lesson 3-3, proportional and non-proportional relationships. Today's TEK, 8-5A, 8-5B. Basically, we will represent linear, proportional, and non-proportional situations with tables, graphs, and equations. This is today's learning objective. Our vocabulary, proportional and non-proportional. A relationship is proportional if its equation is in the form of y equals kx. So if I have something like y equals 3x, then it's proportional. Okay? If we look at it visually and on a graph, we're going to look at something that looks like this. Notice that here, the y-intercept is missing, right? It's like the same as plus 0. That basically signifies that if it's proportional, if it is it has direct variation, then it's going to go through the origin. Please note the misspelling right here. That should have been an O right here. Okay? Let's go on to non-proportional. Basically, if it doesn't fit into the form y equals kx. So what about this? Is this proportional? Yes, it is. It is actually proportional because k, your constant of proportionality, is just -3. But here, what if I do this? Now that I have a y-intercept of 5, it is non-proportional. And this would be a line that looks like this. Let's see, something that looks like this. Right? Notice how it does not go through the origin. Any questions? Please make sure you write down all questions so that we can answer them in class tomorrow. All right. Let's look at our first example. This is example number 1 regarding energy. The table shows the number of miles driven for each hour of driving. Graph the data. What can you deduce from this pattern about the relationship between the number of hours driving h? Okay, so this is the number of hours. Oops. Hours. Let's try that again. Hours driving and the number of miles driven. So which one is independent? Hours, right? Hours driving is independent and our miles is dependent. So typically this is x and typically this is y. I'm going to go ahead and write that outside of here, okay? I've got x and I have y. So what can we deduce? Notice that every single time it's going up by how much? 1 hour. Very good. And every single time here it's going up by 50 miles. Very good. Do you imagine that if we connected these lines, it would go through the origin? I believe it would. Let me kind of show you right here. Boop. So if I had something like this, I imagine that this relationship would probably go right through the origin, right? So this is directly proportional, and I would conclude that we're going 50 miles per hour. So if we write this as, let's see, what can you deduce? Got it. I'm going to say, so in words, that we are going 50 miles per hour. Of course, per hour means how many hours? 1 hour. Did we answer the question? What can you deduce? That's our deduction. Okay. So write an equation to describe this relationship. Okay. Well, again, we had y here, x here. Yes? This is going up by 1. This is going up by 50. Which one is rise? Go ahead and show me rise right now with your body. I can see you. Is your arm moving up and down? Very good. Then rise is associated with which axis? The y-axis, the one that goes up and down. And run must be x. So we know that slope is rise over run, right? And I'm going to go ahead and put my change in y over my change in x. Change in y is 50, and my change in x is 1. Ladies and gentlemen, we have a slope of 50, okay? And if I were to take it backwards to find my y-intercept, at the y-intercept, what is always equal to 0? Remember, it's the opposite. What is the opposite of y? X. X is equal to 0. So what would I have to do in order to get to 0? 0 to 1 is plus 1, right? Same proportion. So that means that this has got to be plus 50. What can I add 50 to and get 50? 0. And this would explain the graph going through the origin too. So my y-intercept must be equal to 0. So now that I have this, and I have this as my slope, I can go ahead and write my equation, right? So we have y equals mx plus b. The y-intercept is the beginning of our story, and that one is associated with b. The slope is also represented with the variable m. Let's plug it in, and we get y is equal to 50x plus 0. I can simplify that. Y is equal to 50x. And if you think about it, 50 miles per hour, right? 50 miles per hour. Well, that's when we read a problem, that word per means that it's going to happen more than once. So we're going to multiply it times a variable, right? And whatever comes after that per, that hour, that's referring to what x? X is the number of hours. Ladies and gentlemen, our equation is y equals 50x. You see how it's kind of all coming together? So did we answer the question? Yes, we did. Use this equation, y equals 50x, to predict the number of miles driven in 8 hours of driving. So again, we have to reference our graph or go back to our previous notes. X was referring to which variable? Hours. And Y refers to miles. So this is just a way of saying X is equal to 8. We're going to plug that in. We know that 50 and X are really multiplying. And instead of X, I'm going to put in 8. 50 times 8 is 400. And 400 what? Miles. Okay, use this equation to predict the number of miles driven in 8 hours of driving. I predict that in 8 hours of driving, we will travel 400 miles. So keep this in mind when you're taking your AP tests, that we reference the unit for each number and we put it in context of this problem. Okay, now it's your turn. I want you to go ahead and check for your understanding. Remember, in class I'm going to be asking for all of your little examples worked out. So graph the data in this table. What conclusion can you make about the relationships between the number of miles walked and the time spent walking? Okay, So I'll go ahead and pause this. Okay, so ladies and gentlemen, the answer is A. As I was going through this, I read, this is nonlinear. Well, I know it's linear because we have a consistent rise over run. Okay, we have a consistent slope. Every single time it's changing by 1, and every single time it's changing by 1.5. The ratio is the same. Even if I had something like this where I had 7 and 10.5, I still know that my ratio would be the same because this is going up by 3. Because normally it's 1.5 over 1, correct? Which equals 1.5. And if I did the same thing here, 3 over 2, my rise over my run, that would end up being 1.5. So those are consistent. This is definitely linear. So if I see the word nonlinear, that's wrong. Not enough information? No, there's plenty of information. Now, inverse. Inverse is the idea that one thing is increasing while the other is decreasing. And both of this is plus every single time, and this is also adding every single time. So if we had something that was adding and decreasing, then maybe we would be looking at an inverse relationship. But you can be inverse and linear. Okay, the next example. Write an equation to describe this relationship between hours and miles. Okay, go ahead and pause it. All right, ladies and gentlemen, your answer is C. Okay? Because if you look at it, your rise is your change in y over your change in x. 1.5 over 1. 1.5. Okay? Let me think. Oh, and also notice that none of them have a y-intercept because if we took it backwards, see how we have the 0 here? We go backwards. I mean, basically it's still 0 plus 1.5 would give me 1.5, and 0 plus 1 would give me 1. So it goes through the origin, and it has a slope of 1.5. Here we have another. Go ahead and pause it and complete. Okay, ladies and gentlemen, welcome back. Of course, the answer is 12 miles. The first thing we have to identify is x hours, right? What variable is that referring to? Well, that refers to x, okay? And we plug it in, and we look at our final answer, okay? Another kind of common sense approach is you can kind of look at your hours and you can look at the number for miles, yes? So when you plug in 8, are you going to get a number that's bigger or smaller? You should get a number that's bigger, right? If you weren't sure which one, where to plug it in, under X or Y, because here we have 1, and we end up with a slightly larger number, 2, and get a larger number, 3, and a larger number. So from that perspective, had you identified it as Y, you would have ended up with a smaller number, and that should have been an alert, okay? All right, example number 2. Write an equation in the dysfunction notation for the graph. Okay, we're just going to write out all the points. We've got this point right here. So that is 1 and 1. See how we go to the right 1 and then up 1, right? The next one, this point, the coordinates for that point are 2 and 4. We could do it again for this one right here. We got 3 and 7, 4 and 10. Some of you might be seeing a pattern already. 5 and 13. So let's figure out, how are we going from one to the other? Okay. One thing that we can look at is, how much is it increasing by? Notice that every single time it's increasing by 3. And on this side, how much is it increasing by? 1. So I know I'm going to have a slope of 3, the change in y, over the change in x, 1. This is going to be my slope. And slope is always located in front of x. So we're looking at something like 3x. Okay? So here we go, 3x. Well, let me see. If I have 3 times that, I got 3x. Okay, but 3 times 1, and I end up with 3, right? Let's see. 3 times 2, 6. 3 times 3, 9. 3 times 4, 12. And 3 times 5, 15. So, I'm looking at this number right here, these set of numbers, and I'm comparing them to my red numbers under Y. Are they the same? No. What is going on? How do I get from 3 to 1 and from 6 to 4 and 9 to 7 and 12 to 10 and 15 to 13? Do you see it? What am I having to do every single time? If you said subtract by 2, yay, you're awesome. Minus 2, minus 2, minus 2, minus 2, minus 2. Let's take a look at it. 3 minus 2, use your fingers and toes, is 1. 6 minus 2, 4. 9 minus 2, 7. 12 minus 2, 10. And 15 minus 2 is 13. Do our numbers match? Absolutely. So I'm going to take my 3x, because that's what that was, right? And I'm going to subtract 2. And that equals to y. Ladies and gentlemen, my equation is this. Y is equal to 3x minus 2. You just wrote an equation. Congratulations. Again, make sure that any questions you have, please write them down so we can answer them in class tomorrow. Okay, now your turn. No problem, right? You got this. You can identify an equation from a graph. So, go ahead and pause this. Okay, ladies and gentlemen, there's your answer, D. We picked 2 good points. How many lines have to touch before we have a good point? 3 lines. Very good. We identified our slope. We identified our y-intercept, and we plug them in. Is this proportional? No, it's not, because it has a y-intercept, the +1 at the end of the equation, and it does not go through the origin. So please take note of that. Again, because we have the +1 and it doesn't go through the origin, it is not proportional. Okay, that's it. Easy, right? Hope you had a great time. I will see you tomorrow in class with this completed. Those of you who are doing this at home, I appreciate you so much for doing what you should be doing every day. Thank you. Bye-bye.